welcome to today's colloquium. Our speaker today is Zaanen. He is professor.
Start again.
Okay, I start again. So, welcome to today's colloquium. Our speaker today is Zaanen. He's professor in theoretical physics at the University of Leiden. He did his PhD in Groningen. A6. Okay, sorry. I read that you were spending time in Max Planck Institute in Stuttgart and Bell Lab and various places, and that you are professor in Leiden since 2000, I think. And it's a very great pleasure for me to have Jan here. He's very well known for one of the very fundamental and important contributions to the theory, which I regard as one of the really big problems in theoretical physics, namely understanding high-temperature superconductors. And the talk today will be about the history of the theory in this problem, and I'm sure we'll have more about it. So,
Thanks. That works. That works. Yeah, it's nice to be in Stockholm. It's the first time actually that I visit Stockholm. I've been before in Sweden. I've got a talk which might not be ideal for a colloquium because it's a bit too adventurous for a typical colloquium. In the sense that I want to tell you something which is far from being generally accepted. I also carry out a student colloquium, but I find it fun to tell you this story because it's basically exciting us right now a lot. And moreover, it's addressing really what I perceive as the core problem of quantum condensed matter physics. So you can always take it in as more of a allegory about the core problem of quantum condensed matter physics than a final answer. So they don't take it as, absolute scientific fact and more stimulating thought. So the title is very well criticality, and that is what I want to tell about. When it comes to original contributions, much of the work is due to a very, very smart postdoc from Kruger. So in a way it's also his story, or probably even more his story than mine. It's ambitious. You might know about the Gross list. It's by David Gross, who got the Nobel Prize in 2004 for asymptotic freedom in QCD. And he has been given around the world this is a big list of questions, namely the 14 most fundamental questions in contemporary physics. Like number one is the origin of the universe. That's pretty obvious. 2 is what is dark matter. I understand you have here a big astrophysics department, so that should also be very obvious. 11, what is space-time? Because you have string theory, so you know why this is so obvious a problem. Now, some of my condensed matter colleagues say that David Gross really does not understand condensed matter physics because he's only put one question on his list associated with condensed matter physics, that's number 14. I actually agree with David when you ask what is a real big mystery in condensed matter physics is this one. New states of matter. Are there generic, non-thermal liquid states of interacting condensed matter? I would actually like to formulate it differently. Is there a solution of the thermal sign problem? I don't know if this audience at large knows what the thermal sign problem is. I guess you are all well trained as physicists. So you know about the collective behaviors of large numbers of quantum particles. And you know that quantum statistics is very important. So let's consider a simple question. What is going on in a piece of copper wire? It's forming a metal. And there's this electron system. And we all learned in school that we can understand this electron system in a surprisingly simple way. So, because of quantum mechanics, we know electrons are waves. And they do this job of doing a dispersion as function of wave factor and energy. And then we are supposed to use the Pauli exclusion principle to fill it up. And then we get this Fermi energy dividing occupied states from unoccupied states. And there are characteristic wave vectors associated with this Fermi energy, and they stand up an object called the Fermi surface. And you likely learned in school that when you know about the Fermi surface, you can address all the physics of that metal in a copper wire. By itself, it's completely unreasonable. Why? The electrons are charged particles, and they are rather close together, like an extron. And they interact like hell. Well, this is a picture based on completely independent fermions, so why can it work? This has never been resolved. There's no general theorem saying that when you start out with a large number of strongly interacting electrons and you put them together at a high density, they will form this Fermi gas. It has been kind of inspired phenomenological guess by Landau, that you can pretend that by collective effect, these electrons reorganize such that they get close to the Fermi energy at low energies. You can pretend that you are dealing with a system of electrons having shaken off the electrical charge. They're no longer interacting with each other. But in any other regards, they are like electrons. They're fermions, they carry spin 1/2, etc. And this is a lambda Fermi liquid. So, this is the way we usually deal with fermionic systems. We also deal with them in this way in fundamental physics. Because the Young vacuum is also of this kind. We know one more thing to do with fermions, and the Barling-Cooper-Schiefer theory of superconductivity, that's now 50 years old, is kind of a symbol of that. So we take electrons, or fermions, and we let them interact. And it might well be that they figure out that they bind together in bosonic objects. And then the collective physics is that of bosons. So in BCF theory, it's dealing with superconductivity, and the story is that these lambda mass particles talk to each other via the exchange of phonons, and that makes them attract. And then they decide to form little pairs of electrons called Cooper pairs. They form this famous constant wave function. And these Cooper pairs are bosons because they are formed from 2 electrons. And these bosons both condense, and then you get superconductivity. So this is the other trick we know to do with fermions. We declare them to be bosons. What is so horrible about this? We don't know anything else to do with fermions than these 2 tricks. Declare them to be a Fermi gas, or assume them to be turned into bosons. When you're dealing with bosons, it's a completely different story. The theory of bosons can be regarded as solved in essence. And the reason is, we can use the enormous powers of the path integral method. The path integrals, they will come back in this talk, so when you don't know them, let me explain quickly what the essence is. All you have to do is to pretend that the world lives in d plus 1 dimension, where the extra dimension is preferably imaginary time, that is time to the square root of -1. And then in this Euclidean space-time, you can just stick a system that behaves like a statistical physics system. And statistical physics is an enormously powerful methodology. When you're dealing with equilibrium statistical physics, there are no mysteries. It can be solved in principle by working hard. Henceforth, we can classify all possible forms of bosonic matters by just solving these statistical physics exercises in space-time. And then we have to translate them back to real time, etc., but we know in principle how to do it. Henceforth, with bosons we are very mighty. With fermions we can only do 2 things. Now the question to ask is, could it be that fermions could do something else than playing Fermi gas or affect the bosonic system? And we have no answer to the question at all. We have no clue. A neat way of expressing the puzzle is let's see what happens when we try to deal with fermions in a classical formalism. Already Feynman realized that you run into a horrible problem, because thermal statistics translates into a recipe that you have to wind world lines around that imaginary time axis. And depending the way you wind them around that imaginary time axis, you get plus or minus signs in your effective partition sum. This is no longer a probabilistic problem, because only when these are all plus signs, it's like a Boltzmann sum, and you find back to statistical physics. When you have these minus signs, you get horrible cancellation between the positive and negative contributions of these pseudo partition functions. And the bottom line is this is an empty complete problem, mathematically extremely ill-behaved, and it cannot use this classical method. This is the minus sign problem, and this minus sign problem is making us blind for the general nature of fermionic matter. So why is this an issue? To Marshall believe at all these instances when we cannot make sense of phenomena occurring in quantum nature, at least in the condensed matter context, we are basically facing this minus sign problem. And I am of some opinion that the best example of it is actually ITC subconductivity. So the story of ITC, it started a little more than 20 years ago with the discovery of these two gentlemen of subconductivity in the ceramic copper oxides, where suddenly the subconducting transition temperature jumped up from about slightly more than 20 degrees centigrade after nearly a century of work to temperatures as high as 140 Kelvin. Now, shortly before this happened, there was a widespread belief that subconductivity could not occur above a temperature of about 30 Kelvin. Nowadays, we would say probably 40 or 50 Kelvin. We have learned a bit more since then. But still, it's completely unimaginable that based on this BCS thought, you can afford to have subconductivity at a temperature as high as 140 Kelvin. The reason being really that a Fermi liquid doesn't allow you to get at these high temperatures. You cannot figure out a mechanism based on a Fermi liquid as metal state, making it possible to form these Cooper pairs and let them condense at such high temperatures. In 2006, there was sort of the 20-year anniversary of the high-DC subconductivity problem. It got quite a bit of attention in the, somewhat popular scientific press. Nature Physics dedicated their large volume to this celebration, and that was a very nice feature. It was very well done. And I quote the editorial on page 138. The diversity of theories for the mechanism of ITC is explored by some of the leading thinkers, including Philip Anderson, David Bynes, and Jan Zaanen. Yeah, that's me. Now, the reason that I got this honor was basically because I wrote down rather sharply this agnostic attitude. That is, we have no clue what's going on, and therefore I got a lead in this feature. The bottom line is that lot of very, very smart people got obsessed by this problem, and they really worked very hard on it, and they all failed, including this little exhibit of Nobel Prize laureates, including Frank Wilczek. He's not an honest matter guy. Now, what's the reason that all these characters failed? I think it's really the minor sign problem, because we haven't solved this fundamental methodological problem. We are blind. So what is the problem in ITC? So the subconducting state is eventually something which I don't perceive as exceptionally mysterious. I think we understand it. And this picture of electrons binding together in little Cooper pairs that both condense is still valid, although there is more organization in that world than in a simple PCS superconductor. But in essence is about bosons, and I don't think it has big secrets. The secret is really there in a normal state, in a metallic state above the transition temperature, so you can have this high precision stuff in your hand and look at it. And there is the enigma. And the enigma is that we can no longer think in terms of this Fermi gas picture, this Fermi liquid picture, metaphorically like this foggy, structureless reality. Instead, we know actually for sure that the electron will in these ceramic copper oxides is more like a very, very crowded disco, where the role of humans is taken by electrons, and these electrons have to dance because they are quantum particles. But it's very crowded out there, so they cannot dance on their own and freely. When they just dance on their own and freely, they will stand on the toes of neighboring electrons, and these neighboring electrons will start crying to them. And therefore they have to dance in very collective ways that are entirely different from this Fermi gas picture. Out of this, in ways I don't comprehend yet, comes a new state of fermionic matter that we don't really claim to fully understand. You will hear ideas about it. And it is a state of fermionic matter that's no longer characterized by the scales of the Fermi gas, the Fermi energy, and the Fermi surface, or the Fermi momentum. Instead, it's a scale-invariant state of fermionic matter, and this is called a quantum critical state. And I will present what is to my own strong opinion again, unambiguous empirical evidence for the existence of this strange state of fermionic matter. We cannot understand this state as a Fermi gas or either a state that's like hidden bosons. And we need to crack the fermion minus sign problem to understand it. And that will be basically the morale of this talk. This is not standalone. The same problem occurs in a related but yet different context, namely at the center of modern heavy fermion physics. So heavy fermions are these intermetallic stuffs containing all kinds of strange elements. And they're famous already for a long time for the fact that they do form fermion liquids, but the nanoparticle particles can be as much as 1,000 times as heavy as electrons, which is weird. The more recent development is that it seems generic that in all of these systems you find these phase transitions where you go from one fermion liquid to another. And as a function of temperature, you find here, so this is a function of a magnetic field or something, as a function of temperature, you find here a regime, which is again dramatically different from a Fermi gas. And that's actually quite similar to what we find in cuprates. And I'll come back to this later. So, here's then the plan of the talk. I already introduced the fermion sign problem and why we should worry about it. I will first do a very short advertisement for a talk I will give tomorrow, which is telling you something about groundedness physics in these electron systems in cuprates. Then I will go basically very, very phenomenological and make a very strange case that the high-precision metal is actually a Planckian dissipator, and that tells us that it's a quantum critical state. And then I will tell you about a way around this fermion minus sign problem, where we have managed to discover a fermionic quantum critical state. We don't know if this is the whole story, but at least we get somewhat beyond this minus sign problem. At the end, I will say a couple of words why we can read from this part about the fermionic quantum criticality that there are good reasons that subconductivity can happen at high temperature. Okay, so first the advertisement, this will be very short. I don't know if you have seen this before. It's kind of the icon of how you see subconductivity. It's the phase diagram. So it's basically spread by two axes. An axis called doping and an axis called temperature. And the story of how you see is you start out with an insulator, and this insulator is a mock insulator, and it's insulated because of this crowdedness of the electrons. It's so crowded that electrons can no longer move. Then you dope it as you dope semiconductors, and you relieve the crowdedness a bit, and they can start to move, and then all kinds of strange things happen. First you went into a phase, or whatever, a state of electron matter, that's called supergap. Then at a point, superconductivity kicks in, and here starts to rise, and here's at maximum. When you go much further, a set of normalcy returns, so it might well be that when you're strongly overdoped, meaning superconductivity goes really down, you recover the Fermi liquid physics. Right at optimal doping, there is this very strange metallic state. I call it solute, it's called a critical. My talk of tomorrow is basically about this underdoped regime, where superconductivity is not great. And there something happens which is now called striking things, at least by me. And striking things are much of a symbol for this disco physics, for the fact that the electron system is very crowded, and when you let the electrons do the quantum mechanical dance, they do different things than the Fermi liquid. What they do is kind of a quantum mechanical pattern formation. That's one way of memorizing this. I will explain tomorrow in some length that there are now very fanciful experiments where you can see directly these sort of electronic patterns that are formed through this calculus physics. And when you want to know more about it, come to my talk tomorrow at 11, I believe. Right now, I won't tell anything about it because I'm lacking the time. Well, I want now to turn to a story which I take as fact. It's based on experiment. So this is really about this strange metal, that optimal doping. This we forget. And something very strange is happening there. To really get this into the minds of polyphysicists, I have invented myself the word Planckian here. Because when you say Planck, physicists sort of wake up. So, Planck scales, you know what they are. You have a phenomenon called gravity. It's figured out by Einstein. It's about matter working space and time. It's characterized by dimensions, Newton's constant and the light velocity. When this would be all, we could simply go to Paris and change the dimension of meter in a second. And the theory wouldn't care about it. It would stay the same in general relativity. However, there's also a natural constant called Planck's constant. And special because it carries the measure of action is energy times seconds. Now when you now combine the dimension of gravity with Planck's constant, you can point at an absolute scale which is either a time scale or length scale or energy scale, whatever, expressing time. It's like 10 to the minus 42 seconds. And the meaning of this time is that a classical phenomenon of gravity has to meet quantum physics. And now the specialty of this problem is that they don't like each other, so something new has to happen. That is the meaning of a Planck time as we know it. Let's now look at a different phenomenon. The phenomenon of dissipation, that is, useful work, is turned into useless heat. And this takes a characteristic time that's called the realization time. Now, dissipation is a purely classical phenomenon. It only happens at a finite temperature. Henceforth, the characteristic dimension of this classical phenomenon is temperature, and you can express that in energy like multiplying it with Boltzmann constant. Given that h bar exists, there is now a unique timescale, because h bar carries the dimension energy second. When you divide it by energy, you get a time. Claim the shortest possible relaxation time under equilibrium conditions is equal to h bar divided by kBt. You cannot dissipate work into heat faster than this for fundamental reasons. Now the second claim is that in order to reach this Planckian dissipation, you need to have that the underlying quantum dynamics in your system is scale invariant, is critical. And that's a less obvious thing. I'll explain it. To comprehend this, the only way I can comprehend it is again leaning on the past integral formalism. Quantum critical dynamics means that in this Euclidean space-time world of quantum physics, you have a scale invariant stuff. When you now look at finite temperature, it's kind of a postulate type of thing. What you're supposed to do is, you're bringing temperature as we know it by making the length of this imaginary time axis finite. It's just fundamental. I mean, when you take this as a recipe, you recover all of quantum statistical physics. This way, it's very simple. So, the length of the imaginary time axis at the finite temperature is h bar divided by kVt. And that breaks the scale invariance, because it's like a finite size scaling, as you know it from the Wilsonian renormalization group theory. So why do I take this picture of this vegetable? This is basically a joke. Physicists know what fractal means. What I didn't quite know is that you can actually eat fractal things. And this this cauliflower called Romanesco. And when you have a fancy vegetable shop, you might find it. In Holland you have them. So it just looks like a cauliflower, but let's take a little piece of it, amplified by factor 10. Okay, it still looks like a cauliflower, so let's take a little piece of it and amplify that by factor 10. You get to see this. Again, you repeat your scale, rescaling operation, take a little piece, amplify, you get like this. So I perceive this as rather spectacular. You can go to the shop, buy this stuff, and then eat it. And when you the tooth go through it, realize that you are crunching all these fractal structures. Okay, so put this kind of stuff in space-time, and what you get. So we know exactly how to calculate physical properties from the Euclidean space-time Pascal formalism, or thermal Pascal formalism. And the bottom line is that two-point correlation function in this Euclidean space-time translate in dynamical system abilities that live in our world, that can be measured by experimentalists. But you have to do a necessary operation called analytic continuation or grid rotation, where you have to go from imaginary time to real time, and there is kind of a big information problem because things in imaginary time are very smooth and become very peaky in real time. This gets especially a horrible problem when you look at measuring times that are light compared to the length of this imaginary time axis. So what to think? When you measure at the time, it's like 1 over frequency, which is large compared to the size, the temporal size of the space-time box. Now, there's an answer. Mostly due to Souvir Sasted, sort of the guy owning this whole subject of quantum phase transitions. He wrote a very influential book about it. He's now at Harvard. And Souvir showed that generically in this regime, when you are quantum critical and you measure at frequency small compared to temperature or times large compared to 1 over temperature, or it's divided by kVt, you actually find a purely classical realizational dynamics. Meaning, you give the system a kick, and if there's like water or syrup or something, this energy is eventually dissipated in heat. There is now this relaxation time there. And so we show that generically, in all cases we considered, when the system is quantum critical, the relaxation time is like a constant times h bar divided by kVt, where the constant is of order 1. It can be like 1 over 2 pi, or some say it can be pi, but it is of order 1. So why is this? This is, as I said, the fastest possible relaxation imaginable in nature. Why is that? That's actually very simple. When you would like to relax faster than this, it would mean that you would end up inside space-time, Euclidean space-time. And Euclidean space-time is coding for unitary time evolution. It's purely quantum mechanics. And unitary time evolution is characterized by conservation of information and cannot produce entropy. Henceforth, when you want to realize faster on shorter times than this, it's forbidden because you need coherent quantum dynamics. That's simple. A bit less simple is that you can only find this maximal relaxation when the system is invariant under scale transformations inside space-time. Now, the reason for it is kind of simple at the end of the day. At the moment, the quantum dynamics has a scale. This scale dilutes degrees of freedom. It's like, you have a solid and you have phonons. And phonons are not very many degrees of freedom as compared to quantum typical degrees of freedom. And therefore, dissipation has to take longer. So, to maximize dissipation, get rid of scales of opinions in the quantum dynamics. Now, a typical example is, how does dissipation work in a Fermi liquid? This thing of Landau. You might have learned this. It's called that the conductivity in a Fermi liquid goes like plasma frequency squared times the inelastic scattering time. And inelastic scattering time is just this relaxation time, but now in this gaseous language. Then you can look in the books and you find out that this inelastic time is h bar EF divided by kT squared. What is it? It's Planckian dissipation time, h bar divided by kT, multiplied by the ratio of EF divided by kT. In order to speak meaningfully about a Fermi liquid, EF has to be large compared to kT. Henceforth, in a normal metal, it takes the time longer by the ratio of EF over kT than the Planck time to relax your work into entropy. How does this work in high-energy cuprates? I like to work as experimentalist, and this was kind of big fun. This is my friend von der Maan, who is specializing in measuring optical conductivity. In order to nail this down, you need to know what the electrical conductivity is at finite frequencies. For technical reasons I don't want to go into. But it took some time before it was figured out. It appeared in Nature in 2004. The bottom line is that Dick went out and looked at this regime where measuring frequencies are small compared to temperature. You need for that a lot of fancy optical machinery. And he actually managed to get a good scaling collapse. And the bottom line is that indeed, in this normal state of optimally doped cuprates, you find a relaxational dynamics in this regime where frequency is small compared to temperature, characterized by a relaxation time, which goes like A divided by h bar divided by kT, where A is 0.7. In other words, the high DC normal state is doing Planckian dissipation. Planckian dissipation has to mean, because I only use very general arguments, that this metal is controlled by an underlying scale invariant quantum dynamics, meaning that metal cannot know about the Fermi energy. And I guess anybody who has thought about metal is like, what are you talking about? Because there's always Fermi energy, not in high DC. Okay, I hope I convinced you that something interesting is going on there. There is this other story, and in a way, this heavy thermal story is even more clear about what's going on. So, this Planckian dissipation thing translates in high DC subconductivity in a famous and old result, namely the linear resistivity. When you look at the resistivity, electrical resistivity as function of temperature, you have this very, very straight line. You don't see that in any other normal metal. Normally, the resistivity is some interesting function of temperature for various reasons. And I can see this crazy straight line which extends up to the melting point of these periodic crystals. Let's now go to heavy thermal systems. So the typical deal is that you start out with this heavy thermal metal, where you have these greatly heavy gas particles. Then you take very zero temperature control counter like a magnetic field or a pressure. And then you get a sudden change. And then you look at what's going on when you go up in temperature. And you find, again, a linear resistivity. This color coding is about the exponent associated with the resistivity. And yellow means it's 1, and blue means, or purple means it's 2. So in a thermal liquid you expect t squared. Here's a t squared 2, and right at this special point it becomes t, linear in t, so you have the same resistivity. In these systems we know a bit better what's going on. Because there is very firm evidence that this is a phase transition where you go from a metal with one type of thermal surface to a metal with a very different type of thermal surface. And it's a completely continuous transition. So when you write here, neither this thermal surface nor this thermal surface is true. Instead, something critical made out of Fermi surface is true at this point. But how can we think about something critical made out of Fermi surface? Because Fermi surfaces are like this or like that. How can it be a critical one? Point is that Fermi surfaces are not in a library of critical phenomena. This is again revealing this minor sign problem. Okay. I hope I have convinced you that there are reasons coming from experiment that imprint on us theoretical physicists that we are dealing with something which is completely unknown to us, something which we cannot handle with any methodology like rotation. Because we are facing this minor sign problem, we have now detected a state of fermionic matter that is neither a Fermi gas nor a bosonic state. It's a critical state of fermionic matter. And we cannot describe it either with Fermi gas language or with bosons. And now I'm going to switch gear and tell you about a way to think about it. And I'm quite confident that we get something right. We can think differently about it. And it's like, taking you in a new way of thinking about fermionic many particle physics. So, it's about trying to use a particle. And I already explained this business, that when you're dealing with fermions, that depending how you organize these world lines, we get plus or minus signs in front of something which looks like a Boltzmann factor. And because problem is non-probabilistic, you don't know what to do with it, and it makes you blind. Now it turns out to be an alternative way of writing this fermionic particle. And to kind of explain how that works, I first have to step back to a much more elementary level you hopefully like, because everybody has learned this in the very beginning of learning quantum mechanics. Namely this business that bosons of fermions tell you about the sign of the wave function pending the way you exchange particles in your Schrödinger type many particle wave functions. So when you have a fermionic system and you exchange the particles, then the wave function is supposed to change sign. Remember, this is a way to writing the Pauli principle. So let's take a simple example. We simply stick in plane waves in a slightly determinate and we describe a fermionic gas. And let's now start to ask a couple of questions about the workings of this wave function when we discuss fermions. First, for your orientation, we know from the Pauli principle that two particle positions cannot be coincident. A wave function lives in configuration space, meaning it lives in an n-d-dimensional space where n is the number of particles and d is the number of space dimensions, because that is all the coordinates of these particles. In the space you can now define a Pauli hypersurface, that is the hypersurface hanging there in this configuration space, defined by the fact that particles are coincident. This is a hypersurface having dimension nd minus d, because you have d constraints. You can visualize this a bit by just making a cut, and let's assume that we're living in two space dimensions. And we just sprinkle the particles at arbitrary positions, except one particle, which is the yellow one, and that we use as a test particle. So from the viewpoint of this particle, all the green dots, position of other particles, lie on this Pauli hypersurface. This is insufficient condition for the Fermat statistics, because we know that we can have sign changes also when particles are not coincident. We just have to exchange them. Henceforth, you can also identify in configuration space a hypersurface associated with the sign change of the wave function. When the wave function changes sign, it has to have a node, it has to be 0. Because there's only one constraint out here, is this one minus sign, this is an nd minus 1 dimensional space. The way to visualize it is, we have here a test particle, and when we put it here, the wave function 6 is positive. Then we move it while keeping all other particles fixed at the other positions, and a sign change happens, and it goes to red. And so this is a node, a cut through this nodal hypersurface, a two-dimensional cut, showing you where the nodal surface lies. And surely the Pauli hypersurface is coincident, is a subsurface, a submanifold of this nodal surface. Okay. Knowing this geometrical structure, I can now quickly explain you a result due to David Zaanen. David figured this out in 1990, and he didn't get much followers. His people, his students, etc., are using it now quite a bit all the time. But David figured out an alternative way of doing fermionic fascinations, and you can prove it. It's strictly the same as doing the original Feynmanian definition with the minus signs. I don't know how to explain this in detail, but I can give you sort of a visual picture of how it works. The bottom line is that you can do basically a bosonic fascicle, which is like physics, but you have a constrained structure. What you're supposed to do is sprinkle a configuration of world lines, and then you need to test if it's a finite constraint. And the constraint is kind of simple. Take one particular world line you like, this your test world line, the yellow one, that looks around itself and sees all the other world lines of these other particles. And now these other world lines of these other particles are connected by this nodal surface. When this particular yellow world line goes through this nodal surface, reject this configuration world line from your pseudo partitions. You understand this? So what you're not supposed to do is just your bosonic fascicle and you feel very mighty. But you have now to dress this up. This is in fact geometrical constraint structures. But you would know the nodal surface is basically the same nodal surface as in the fascicle. Not quite in this picture, but I don't want to torture the subtleties now. You can in principle solve the problem. The problem is still that in order to determine the nodal surface, you have to solve the full constraint fascicle. And this turns out to be again an NP-complete problem, mathematically ill-defined. However, you have gained it. What you have gained is that you have now coded the fermionic physics in terms of normal bosonic physics where you feel very mighty, plus a geometrical structure, namely this nodal surface. And the nodal surface is, just a manifold, just like a tent sheet. And we can think about tent sheets. Tent sheets have general properties, they have topology, for instance. Now the story continues, so David Zeppeli figured this out in 1990. But it didn't really fly that far, and the main reason is that all the novelty of fermionic physics is not coded in this nodal surface. But this nodal surface by itself is a rather boring thing, and this is kind of a nice demonstration of it. You start out at 0 temperature, and it's again the same picture as before with our blue and red, so the lines are the nodal lines. And at 0 temperature, you have this degenerate Fermi gas, Fermi gas. You can also define it easily at high temperatures, and this is high temperature limit. This is like a completely non-interacting classical gas. And not that much is happening with that nodal surface. Okay, it looks a tiny bit different, it's a bit more cornery. So, when thermal physics is about this kind of geometrical stuff plus nodal bosons, what heck do you learn here? Nothing. Now, what you learn from these kind of nodal surfaces associated with Fermi liquids is that they actually carry a dimension. Their geometry, and geometry can carry dimensions. In the case of the Fermi liquid, it's kind of a simple thing. You have a typical size for the pocket in which one particular root line is confined. It's not so strange because it's an n-1 dimensional manifold living in n dimensions. Henceforth, there has to be a characteristic dimension associated with the nodal hypersurface. And it turns out to be just the interparticle distance. So the average size of such a nodal cage or nodal pocket is the interparticle distance. What has this to do with the physics of the Fermi gas? It's kind of fun exercise. We're dealing now with bosons or normal quantum mechanical particles that live in little prisms. They cannot get out. And we know what happens with particles living in little prisms. They acquire a 0-point energy. So let's calculate that. So we use typical statistical physics language during this class intervals. And what you're supposed to do is calculate the typical spatial fluctuation associated with a distance tau in a time direction. Now, it's easy to calculate that because these road lines are just like polymers, elastic one-dimensional manifolds. Converting it to continuous, you get that it goes like 2 times the number of space dimensions, h bar divided by 2m times tau. Now, given that they live in this little prism, then this spatial fluctuation, because of order of the typical prism size, phase size, which is r squared s, then a collision will occur. Now, what is this collision time? We just invert it, and the collision time is 1 over 2d times 2m divided by h bar times n, the particle density, to the power minus 2 divided by d. So there's an energy scale associated with this time, which is h bar divided by tau c, plug things in. This is exactly the Fermi energy. So the Fermi energy in this language is nothing else than this confinement kinetic energy. The fact that our little fermion world lines are lived in prisms, and therefore here kinetic energy is pushed up. Okay. Now we've learned actually something important, because we have learned how to think about the scale of the Fermi gas, the Fermi energy, in a purely bosonic language, very filmighty. In order to defeat the Fermi energy, that does at hand in high PC and have the fermions, we have to get rid of the Fermi energy. Henceforth, the nodal surface has to become a fractal geometry. It has to forget that it has a characteristic scale. Henceforth, this nodal surface has to become like the cauliflower. Okay. So, now we are facing a problem because I have now figured out how to construct a critical fermionic state. Then I have to figure out somehow a nodal surface that's fractal. But to write it down, I need somehow the solution of the problem. And now we, Frank and me, had sheer luck, because we figured out an ansatz doing it to us. Now this is actually again interesting. It goes back to an old idea, again, by Richard Feynman. Somehow we meet all the time Feynman in this affair. and it's called backflow wave functions. And something Feynman figured out to explain local minimum in helium-4, and I don't want to explain you that story. The idea of Feynman is basically like, when you do hydrodynamics, you have a very well-known phenomenon that's called hydrodynamic backflow. When you move a stone or something through water, and you move at a velocity small compared to the velocity of sound of the liquid, then the liquid behaves like an incompressible medium, and when you move the stone like this, the fluid has to get out of the way of the front of the stone, henceforth it has to build up a flow pattern exactly compensating for the motion of the stone. Which is finally figured out a way to do it quantum mechanically. And it's a very charming thing, it's called a backflow wave function, here it is, and the bottom line of it is, you can just pretend it to be like plane waves, except that the coordinate is now a collective coordinate, it's the coordinate of the stone, plus the sum over the difference between the coordinate of the stone and all the particles in your system divided by this r cubed. So it's a collective coordinate. What you now can do is take this wave function, put it in a slightly determinant, and you now describe a fermionic system made out of these backflow particles. Now you can argue that this is related to describing as physics. You can think disco here. When you want to move through the disco, it's very tangent. When you move like this, or you dance like this average direction, then all this other dancers have to move back. So it has to do with this groundedness or modness physics. So, I got Frank as a new person, and I told him, Frank, put this in a computer, make plots of the nodal surface, and show me how it looks like. Works very good, and in no time he came to my office with this picture. Same coding, yellow test particle, green other particles at the other positions, and blue and red being positive and negative wave function. So this picture looks interesting. It really looks interesting when you just take a bigger field of view, more particles. And this is, I guess, a nice looking picture. Why is it nice? Let's take a little piece of it and amplify it by factor 10, and you get to see this. A fractal nodal surface. Okay, I can cheat you a bit, I'm running out of time, so let me do this quickly. So you can now go to the professional books. I don't know if there's any specialist in this room. It's basically study Coswager. And there you find tricks to really nail down if your geometry is factor or not. And that's what Frank did. And he figured out that for backflow, the dynamical backflow, the dimension of the nodal surface is actually hanging right in between NB minus 1, dimension of it, when it is like a fermi liquid, and NB. So the fractal nodal structure is much more space-filling than the nodal surface of the fermi liquid. You can actually play, this is backflow. So it turns out it has two length scales. One of them is ultraviolet cutoff, not important. The other one is IR cutoff. And the story is that when you put at zero, you find the fermi liquid. When you start to make it small but finite, you start to see little things happening around these other particles, and these get more and more and more. When this backflow range gets larger than the interparticle distance, this nodal surface switches to a fractal. This is probably our most extensive result up to now. So you might know that fermi liquids are characterized by the famous jump in n of k, the momentum distribution function of momentum, as function of momentum, signaling the presence of a Fermi surface. So look at the black line. This is for no backflows, this is Fermi gas. You're like occupied, and then bang, you are unoccupied. And here Frank has figured out what happens when you increase this backflow range. So what's happening is that when you increase this backflow range, this jump gets less and less. In the Fermi liquid context, this means that the mass of the particles is increasing, the jump gets less, then at the point where the backflow turns hydrodynamic, turns like this, you find that the Fermi surface, or the German LFK, has completely disappeared, and you have here some power law momentum distribution. It's kind of interesting because you can now look at this jump, which is like the inverse mass, as functional backflow rates, and actually doing a beautiful sphenical magic. It is really like the behavior of a correlation length when you're dealing with the normal critical state. This is the first time in the history of mankind that someone has demonstrated that you indeed can achieve a Fermi liquid criticals. This backflow business is doing it to us. Okay. Let me end in 2 minutes with telling you why this might actually contain the clue to the problem of the height of TC in high TC superconductors. That's also unreasonable. Let me start out with a very general remark. It's again my strong opinion. I don't think that anybody else working on high TC is sharing this opinion, but it is whether I feel very strong about it. So when you ask any high TC person why is TC high, he will say, because there is superglue binding the electrons in pairs. This is actually nonsense. This is just wrong. It's a wrong answer. Why? We know a hell of a lot of things about the high TC superconductors, and a superfluid state is actually a very whimsical superconducting state. It's a very bad superconductor. Sounds strange. Now we know it because the real missile of the superconductor is not set by TC, it's set by the superfluid density. And superfluid density is the equivalent of a spring constant when you're dealing with a piece of crystal. Now it turns out that the superfluid density is very low in high TC superconductors, much lower than in conventional superconductors. So it's very easy to bend and twist the high TC superconductors. It's like when you're dealing with crystalline matter. When your strain constants are very small and you have very soft phonons, then your crystal has not a great cohesive energy. It's like comparing diamond with a colloid crystal. And high TC is more like a colloid crystal, and aluminum superconductor is more like diamond. Now when you have a very soft crystal, you know that its cohesive energy sucks. It's not great. Now, TC is really set by the competition with a state that can carry entropy. Superconductors are not great carrying entropy. In other words, to have high TC, it has to be that the free energy of the metal even sucks more. Now you have to realize that actually in absolute units, the energy of a Fermi liquid is actually very bad. You have to put all these particles in states of high kinetic energy because of the Pauli principle. Now we have learned how to look at it in this different nodal constraint mathematical language. Namely, it's about its confinement energy. Fermions are bosons in cases, and therefore they have a high energy. But when you now put these electrons in this fractal cage, corresponding with a constraint structure which is much more space-filling, right? Remember it was like ND minus half instead of ND minus 1. These four bosonic-like particles are now pushed to even higher energy. Henceforth, a fractal or critical fermionic state has a seriously bad free energy. Henceforth, it allows the superconducting state to take over at another high temperature. Just skip this. And I just skip this. So, here's my conclusion. So, I didn't really go into it. The superconductor looks like, at the end of the day, an object which is quite like a BCS superconductor in the sense that electrons form pairs, and these pairs both condense. They do it in a bit more organized way, likely than in the BCS superconductor. But still, at optimal doping, it looks much like it's a temperature where these pairs pop up for the first time, and then the system goes directly superconducting, at least at optimal doping. The mystery of ITC is really related to this normal state. I made somewhat the point that in these copper oxide metals, the world looks more like a quantum mechanical version of a very powdered disto than this conventional thermal gas view. That makes it possible, apparently, to make this new state of thermal matter that is a critical state, characterized by an absence of a Fermi energy and a Fermi surface. And there are reasons to believe that because this normal state is very different from a Fermi gas and is instead a critical state, the superconducting transition temperature gets enormously elevated, even when you make the superconductivity in its normal means, like let these electrons interact with photons. This is what I wanted to tell you. Thank you for your attention.
Thank you very much for a nice and interesting talk. I was about to say the talk tomorrow is at 11 o'clock at P41. And here we will learn more about the domain models and ITC and so on. Other questions? Comments? Yeah.
This method that you had was described as wave functions. Can you also write down the Hamiltonian?
Yeah, you can write down a Hamiltonian. It turns out to be a horrible Hamiltonian. This arbitrary, endpoint where, n is number of particle interactions in it. So there's no simple relationship between, thinking backflow wave functions and what we know about microscopy of ITC superconductors. It's one of these problems. So the guts here is in a way very phenomenological, right? You can think about phenomenological problems as just like bosons plus this normal surface. Normal surface geometrical object. And then you can use basically any ansatz you wish to figure out if you can get a normal surface being a fractal. So there's something very weird going on with these backflow thermals because there's a hidden single particle representation. You can start out saying my backflow fermions are simply sitting there in a slightly determinant. Then you ask the questions to the electron degrees of freedom, and then you get to see all this weirdness. The fractal nodal surface, etc. And this N of K doing, its adjuncts disappearing. So our working hypothesis is that in order to find that hidden free particle description, you have to write down that very weird Hamiltonian in terms of your original electrons. And so you can construct that Hamiltonian by saying out of just a non-interacting system of backflow particles, and then you do a horribly singular transformation to electron degrees of freedom, and then you get a, extremely singular Hamiltonian. So when you can imagine that you have a nodal surface that's fractal, where your electrons are doing a more normal job, right? And then your Hamiltonian will be more normal. You have to start figuring it out. You have a good feeling that when you look at Kutzwiller wave functions, that there might be also a hidden fractal nodal surface. There's some reasons to believe that.
Are there other questions?
So, can you say anything quantitatively about the size of physique? I mean, is it the right order of magnitude?
Yeah, look, I kind of skipped it. There are several things we know about it now. This is kind of, I think, the simplest way to think about it. So just think your normal PCS theory. You know that TBC is set by this gap equation that contains the particle-particle susceptibility. And G is the coupling constant. Right, so that's telling you it actually found or something. Now, when you start out this Fermi liquid, then the particle-particle susceptibility goes logarithmically. This h bar omega, the final frequency divided by k T. When you stick it in, you get a famous BCS expression for TC, which is like final frequency, exponent minus 1 over G times density space. Now, very generally, this thing is actually set by the presence of the Fermi energy. Now, when you have a critical fermionic state, everything should be power law, including the particle-particle susceptibility. So when that is a power law, regardless its exponent, you get an expression of K Tc, which goes like 1 over G times N naught to the power of minus 1 over beta. And surely, for everything else the same, like X bar omega and G the same, this will give you a much higher Tc than this one. That's a way of beating this BCS exponent. And whatever you think, this should be very good for raising TC. Still believe in BCS in essence.
Is this restricted to dimensions bigger than 2, or could you say some? Is
You
there
mean
an
this-
adaptation to one-dimensional system where you could compare?
Yeah, I mean,
a liquid behavior?
There's actually one-dimensional physics is the ideal context to start explaining this. And let me just get back. Because this constrained classical language is kind of the thing we do all the time in all dimensions. Where am I? I want to get back to say this slide. Or, no, this one. So why is fermionic statistics in one dimensions in a way unphysical? Why is it so that you can always go back and forth between fermions and bosons in 1D? The reason is simply that in 1D, the nodal surface coincides with the Pauli surface. Right? So ND minus D becomes ND minus 1 when D is 1. Meaning that the nodal surface is attached to the particle coordinate. Right? And then you know that fermions turn into hardcore bosons. They simply cannot pass each other. When you go to any dimension higher than 1D, this now shows strips of life. It's not that the particles cannot move when they meet each other. No, they have this kind of ghostly surface connecting each other. And that takes a role of the hardcore condition in one dimension. And so it's very similar to, vocal fermions and hardcore bosons in one dimensions, but now in higher dimensions you have to pay the price of its own surface that has a life of its own, making it in principle richer. And you cannot make this fractal nodal surface in 1D.
Okay, so if there are no further questions, let's thank you.